Hi from Tokyo, Japan, and welcome to Jeremy's IT Lab. In this video, we'll cover LACP, Link Aggregation Control Protocol. LACP is an industry-standard Ether channel negotiation protocol, and like many standard networking protocols, Cisco's proprietary solution, PAGP, came first. Then, LACP was developed as an industry-standard equivalent. These days, even in Cisco networks, LACP is the most common choice. Here's what we'll cover. We'll start with an overview of the basics of LACP, including some differences with Cisco's PAGP. Then we'll take a look at the messages LACP sends to negotiate and maintain Ether channels. We'll then move on to examine LACP's timers. Like PAGP, it has a few timers to control how often the switch sends messages, how quickly it ages out neighbors, etc. Next, we'll look at the minimum and maximum link features of LACP. And finally, we'll cover the LACP system and port IDs, what they're used for, and how to configure them. Okay, let's get started. First, let's cover some basics. This will look very similar to the first slide of the previous video on PAGP. Link Aggregation Control Protocol, LACP, is an industry-standard Ether channel negotiation protocol, combining multiple physical links into a single logical link. Like PAGP, it lets switches exchange information with each other, and then form an Ether channel only if they both agree. The rules for the port channel's MAC address are the same as in PAGP. For Layer 2 Ether channel, the port channel gets its MAC address from the first physical port that comes up. And for Layer 3, a unique MAC is allocated by the switch as soon as the port channel comes up. You probably know LACP as 802.3AD, but the most recent standard for LACP is in the 802.1ax 2020 standard. If you want to get deep into LACP, you can get the standard for free from IEEE Explore. Google it if you're interested. 802.1ax covers link aggregation, and LACP itself, as a protocol for negotiating link aggregation, is covered in Section 6.4 of the standard. As you already know, LACP can be configured in two modes, active and passive. A port in active mode actively sends LACP messages to negotiate an Ether channel with its neighbor. And a port in passive mode only sends LACP messages after receiving messages from a neighbor in active mode. So if I configure switch 2's interfaces in passive mode, at first they won't send any LACP messages. But if I then configure switch 1 in active mode, it will send LACP messages to switch 2, and switch 2 will then start sending its own LACP messages back to switch 1, and they will form an Ether channel if they both agree. LACP messages, also called LACPDUs, are rapidly exchanged during negotiation, and then sent every 30 seconds to maintain the Ether channel. And just like in PAGP, this behavior can be modified by enabling fast mode, as we'll cover later. LACP messages are sent to the multicast MAC address 0180C2000002. This is the Ethernet Slow Protocols MAC address. Slow protocols are a family of protocols that don't send messages very rapidly, and LACP is one of them. Ethernet Slow protocols like LACP use an ether type of 8809, and a subtype of 01 is used to indicate LACP. If you remember the last video, PAGP doesn't have its own ether type, so it needs to use LLC with the snap extension to identify its messages. LACP, being a standard protocol, uses this standard ether type and doesn't need LLC and snap. However, there is the subtype, which is the first part of the LACP message, and it's set to 01 to indicate LACP. Okay, final point. LACP messages are always sent untagged on trunk ports, and of course on access ports too. This is regardless of native VLAN and allowed VLAN configurations. Think back to the previous video on PAGP. On a trunk link, PAGP will send its messages either untagged or tagged in VLAN 1, depending on the native VLAN configuration. For LACP, it's always untagged. In the previous slide, I showed switch 1 and switch 2 becoming LACP neighbors, but let's reset so I can show a difference between PAGP and LACP. If you enable PAGP on interfaces connected to a non-PAGP neighbor, the interfaces will enter standalone mode and operate independently. Let's confirm in the CLI. I enabled PAGP on switch 1, and the interfaces go down at first. Then, after about 10 seconds, they come back up. Do you remember the 10-second timer that controls this? It's the PAGP interface timer. In the output of Show Ether Channel Summary, G00 and G01 are standalone, meaning they each operate as independent interfaces. That's PAGP, but LACP's default behavior is different. If you enable LACP on interfaces connected to a non-LACP neighbor, the interfaces will be suspended, in other words, disabled. This time, I enabled LACP on switch 1's interfaces, and they go down. Then, these messages are shown. G00 and G01 suspended, LACP currently not enabled on the remote port. And this time, Show Ether Channel Summary shows the ports as suspended. By default, they don't operate as standalone ports, instead they're disabled. So that's one difference between PAGP and LACP. If you want your LACP-enabled ports to be able to operate in standalone mode, you can change LACP's default behavior by configuring No Port Channel Standalone Disable on the port channel interface. This will allow the member ports to operate in standalone mode like PAGP. Let's try it out. On port channel 1, I configured No Port Channel Standalone Disable. Then, I enabled LACP on G00 and G01. The interfaces go down at first, as usual, but this time they come back up. And as you can see here, they are now in standalone mode, operating as independent interfaces. Just remember to configure the command on the port channel, not the member ports. Okay, now let's take a look at the messages LACP neighbors exchange. This packet capture shows the exchange between switch 1 and switch 2 as they negotiate their ether channel. I'll point out just a few things. First, notice the destination MAC address is slow protocols. You can see the actual address here, 0180C2000002. And here, you can see the subtype. 01 means it's an LACP message. Wireshark shows the subtype separate from the rest of the LACP message, but it can be considered the first field of the LACP message. We'll see the different fields in the next slide. Here, you can see a variety of flags. Notice how they change as the switches negotiate the ether channel. I'll explain these flags soon. Here are the contents of one of those LACP messages. It consists of a few TLVs, type length value fields. Here's the first TLV, the actor information TLV. This message is from switch 1, so this TLV contains information about switch 1 itself. It includes information like the LACP system priority and ID, the port priority and ID, and those flags I pointed out before. The second TLV is the partner information TLV. This is switch 2's information. Switch 1 includes its understanding of switch 2's settings in the message, so switch 2 can verify that everything is correct. Here are those LACP flags again. They're mostly the same as switch 1's, except switch 1 has the LACP activity flag. So this means that switch 1 is in LACP active mode, and switch 2 is in passive mode. The third TLV is the collector information TLV. I'll briefly explain what the collector is in the next slide. And the last TLV is the terminator TLV, indicating the end of the message. It has a length of 0, so there are no contents. But at the end of the message, padding bytes are added to make the size of the frame exactly 128 bytes. This goes back to earlier versions of the standard, which required LACP messages to be a fixed 128 bytes. To maintain compatibility with devices that still expect this, the current standard says LACP messages should be padded to reach that size. This detail isn't relevant for the ENCOR exam, but it's useful background if you're curious about why the padding is there. The ENCOR exam isn't going to focus on the detailed contents of LACP frames, but it's always good to deepen your understanding. To finish up our look at LACP messages, let's see the different flags it uses. First, the LACP activity flag that I mentioned before. 0 means passive mode, and 1 means active mode. Then there is the LACP timeout flag. 0 means the port expects slow hellos, and 1 means the port expects fast hellos. I'll cover this timer in more detail in the next section. The aggregation flag shows whether the link is eligible to be part of an Ether channel. In all of the packet captures I've seen, this flag is always set to 1, but there could be some errors or misconfigurations that make a port ineligible. Next, the synchronization bit is set when the port has successfully joined an Ether channel and is ready to carry traffic. The collecting bit is set when the switch will accept incoming traffic on this link as part of the Ether channel. I briefly mentioned the term collector when looking at the collector information TLV. To put it simply, the collector is the component responsible for receiving frames on an Ether channel. Frames received on all member ports are collected and accepted by the aggregated port channel interface. Then there is the related distributing flag. When it's set, the switch will send outbound traffic on the link as part of the Ether channel. As you know, frames sent out of a port channel interface are load balanced, in other words distributed, among the member ports. Next we have the defaulted flag. It's set if the switch hasn't received LACP info from the partner and is using default settings in the partner information TLV. In this case, the partner information will appear as all zeros, like this. This can also occur if the switch stopped receiving messages from the partner and the timeout expired. Speaking of that, the final flag is the expired flag, which is set when the LACP info from the partner times out. In other words, when the LACP timeout expires. So those are the different flags included in LACP messages. When studying any protocol, it's essential to examine its messages, but I wouldn't expect any specific questions on the exam about these flags. So let's move on. Now let's look at LACP's timers. Like PAGP, LACP uses several timers to control how often LACPDUs are sent, how long to keep neighbors in the neighbor table, etc. And like PAGP, you can use debug LACP MISC to view debug messages for these timers. To keep the video a reasonable length, I'm going to focus on just the two main timers, the ones you should know for the exam. The first timer is called LACP TXWhen in the 802.1ax standard, and it appears as LACP P for LACP periodic in debug output. You can think of this as the hello timer. It determines how often the port transmits LACPDUs. It's set to 30 seconds, which 802.1ax calls slow periodic time by default. In debug output, this is called LACP PS, periodic slow. Generally, we call these slow hellos. This timer will be set to 1 second, called fast periodic time, if requested by the neighbor. In this case, it's LACP PF, periodic fast, in debugs. These are often called fast hellos. So that's the first timer, determining how often the switch sends LACPDUs. Next we have what 802.1x calls the LACP current while timer, which appears as LACP C, which stands for current, in debug output. This is like the OSPF dead timer. It determines how long LACP information from a neighbor remains valid after ceasing to receive LACPDUs from the neighbor. This timer is 3 times the equivalent hello timer. So it's set to 90 seconds, called the long timeout time by default. This appears as LACP CL, current long, in debug output. This timer will be set to 3 seconds, short timeout time if configured. And it appears as LACP CS, current short, in debug output. You can configure these timers with LACP rate fast for fast timers, or LACP rate normal for slow timers. Now, what exactly does this command do? It sets the local port's current while timer. Then, the neighbor will send LACPDUs at the appropriate rate. This is an important point. If you configure LACP rate fast on a port, it doesn't mean that port will send hellos at the fast rate. It means the port will request fast hellos from the neighbor. Here's the command in iOS. Notice the descriptions. Fast says request LACP packets to be ingressed at the 1 second rate for this interface. So it means the port will request fast hellos from the neighbor. And normal says request LACP packets to be ingressed at the 30 second rate once the link is established. So once the link is established, the port will request slow hellos from the neighbor, which is the default setting. Just keep in mind that this setting controls how often the neighbor will send hellos, not how often this port will send them. Let's examine fast mode a bit more. The ENCOR OCG, the official cert guide published by Cisco Press, says the following. All the interfaces on both switches need to be configured the same, either using LACP fast or LACP slow for the Ether channel to successfully come up. But after testing on physical and virtual iOS XE switches, this appears to be incorrect. Note that the typical iOS V images in CML don't support the LAGP rate command. So if you want to try the command in CML, you have to use the Catalyst 9000V images, which take quite a lot of resources compared to the iOS V images. Let's try with these two switches, Cat9K1 and Cat9K2. On Cat9K2's G101 interface, I configured LACP rate fast. The others have the default setting, LACP rate normal. To confirm, I first used show LACP neighbor on Cat9K1. This command is like show PAGP neighbor, which we looked at in the previous video. It shows info about the device's LACP neighbors. Here's the output. I've highlighted the S and F flags. S means the neighbor port is requesting slow LACPDUs, and F means the neighbor is requesting them at the fast rate. Cat9K2's G101 has the F flag, and G102 has the S flag. And in the output of Show Ether Channel Summary, you can see that the Ether channel is up. The SU flags next to P01 mean Layer 2 and in use, and the P flags next to G101 and 2 mean that they are successfully bundled in the port channel. So from Cat9K1 side, the Ether channel seems operational, despite the LACP rate mismatch. Now let's confirm on Cat9K2 side with Show LACP Internal. This shows information about the local switch's LACP Ether channels. Here's the output. Once again, I've highlighted the S and F flags. G101 is requesting fast LACPDUs, and G102 is requesting slow LACPDUs. And in Show Ether Channel Summary, we can see that the Ether channel is up, and the member ports have been successfully bundled. So what is the effect of this configuration? On their G102 ports, Cat9K1 and 2 will send each other slow hellos, once every 30 seconds. Both ports have the default setting LACP rate normal. Cat9K2's G101 will send slow hellos, since that's what Cat9K1 side is requesting. But Cat9K1 G101 will send fast hellos, because we configured LACP rate fast on Cat9K2's side, so it requests fast hellos. So these three ports, Cat9K1 G101 and 2, and Cat9K2 G102, will have a timeout of 90 seconds, since they receive slow hellos. Only Cat9K2 G101 will have a timeout of 3 seconds, since it's receiving fast hellos. So the statement above from the OCG seems to be a mistake. Of course, there's not much reason to have only one side or one port of an Ether channel request fast hellos while the others request slow hellos. But the configuration is possible, and it does work. This Ether channel is functional and ready to carry traffic. Now let's move on to look at the LACP max link setting. As you probably already know, LACP allows up to 16 links in a single bundle. But only up to 8 links can be active at once. The remaining links are in hot standby mode, ready to take over if an active link fails. Switch 1 and Switch 2 are currently connected by a 10-link Ether channel, and here's the output of show ether channel summary on switch 1. G109 and 10 both have the H flag, meaning hot standby. So they aren't actively forwarding frames, but if any active links fail, they are ready to take over. But if you don't need 8 active links at once, but still want a high degree of redundancy from the extra links, you can modify the maximum number of active links by using the LACP max bundle command on the port channel interface. And the valid range is from 1 to 8. Let's try it out. On switch 1's port channel 1 interface, I configured LACP max bundle 6. Now, in the output of show ether channel summary, G107 and 8 are also in hot standby mode. Only 6 ports are active, and the others function as backups, waiting to take over if an active link fails. Next we have the LACP minimum link setting. By default, a port channel will come up if there is at least one active link. Of course, a one-link port channel doesn't make much sense, but the port channel interface will be up. You can modify this with port channel min links on the port channel interface. Yes, the max links command is LACP max bundle, and the min links command is port channel min links. I'm not sure why they made the commands different. It would make sense if LACP max bundle applied only to LACP, and port channel min links applied to both LACP and PAGP. But both commands only apply to LACP. There is probably some historical reason for this, but just keep the difference in mind. The commands are LACP max bundle and port channel min links. The valid range for the min links command is 2 to 8. Currently, we have the same 10-link ether channel between switch 1 and switch 2. With the default settings, this will remain up as long as there is a single active link between them. Let's change that. On switch 1's port channel 1, I configured port channel min links 4. Then, let's say there's some issue on 7 of these links, leaving only 3 active links between switch 1 and switch 2. Maybe someone was doing construction and accidentally cut most of the fiber. Who knows? This syslog message appears on switch 1. The port channel is down because the number of bundled ports doesn't meet the minimum links requirement. And here's show ether channel summary. P01 now has the M flag, meaning not in use, minimum links not met. So when would you want to use the min links command? When you don't want a low bandwidth ether channel to remain up. This command forces the low bandwidth ether channel to go down, so another link can take its place. Now let's look at the LACP system ID. Each switch using LACP has a unique system ID consisting of a 16-bit priority and a MAC address, so it's 64 bits in total. So it's similar to the STP bridge ID, which also uses a 16-bit priority and MAC address. And just like STP, the default priority is 32768. And the LACP system ID uses the same base MAC address as STP's bridge ID. It's not a MAC associated with any individual port, but a MAC address for the switch itself. You can view the system ID with show LACP sys ID. Switch 1 and switch 2 both have the default priority of 32768. You can configure the switch's priority with the LACP system priority command in global config mode. The valid range for the priority is 0 to 65535. But unlike the STP priority, it doesn't have to be configured in increments of 4096. The reason STP's priority must be a multiple of 4096 is because the extended system ID, the VLAN ID, takes up 12 bits of the 16-bit priority, so you can only modify the 4 most significant bits. But the LACP system priority doesn't have that concept, so you're free to use any value. The switch with the lowest system ID is the decision maker for which links are active in the ether channel. Sort of like how the switch with the lowest STP bridge ID becomes the root bridge. In this case, switch 1 has the lowest system ID, because although the priorities are tied, switch 1's MAC address is lower. And how does switch 1 decide which links are active? The port ID of each port on switch 1 is used to determine which ports are active and which are standby. We'll cover the port ID in the next slide. But one final note here. The port channel min links and LACP max bundle settings are local to each switch. So each switch independently decides the maximum and minimum number of links it can bundle, regardless of its LACP system ID. For example, if switch 1's max links is set to 6, and switch 2's is set to 4, there will only be 4 active links in the ether channel. Switch 1 doesn't dictate the number of active links, just because it has a lower system ID. But due to its lower system ID, it's switch 1 that decides which 4 links will be active. And as I said above, it's the port ID that determines the active links. So let's cover the port ID. Each LACP configured port has a unique port ID consisting of a 16-bit priority and a port number. Like the system priority, the default priority is 32768. It can be modified on each interface with the command LACP port priority. And the valid range for the priority is 0 to 65535. Like the system ID, a lower value is preferred. Ports with a lower port ID will be active in the ether channel, while ports with a higher port ID will be in standby. But only the port IDs on the switch with the lowest system ID are significant. In this example, configuring the port priorities on switch 2's ports won't have any effect, because the decision is up to switch 1. Let's take a look in the CLI. Here's the output of show LACP internal on switch 1. Since we set the max links to 6 earlier, G101 to 6 are bundled, and G107 to 10 are in hot standby mode. As I've highlighted, all of them have the default port priority of 32768. So why did G107 to 10 become standby? It's because of the port numbers. Each port has a unique port number, shown in this column. But really you can just look at the name of the port. 7, 8, 9, and 10 are higher than 1, 2, 3, 4, 5, and 6, so the higher numbered ports enter standby mode. Now let's try changing the port priority on switch 1. On G107 to 10, I configured a priority of 100. This is lower than the default of 32768, so what do you think happens as a result? Here's show LACP internal again. This time, G103 to 6 are in standby. G107 to 10 are active because of their lower priority, and G101 and 2 remain active because they have lower port IDs than G103 to 6. So you can use the port priority like this to control which ports are active in an ether channel. Before we finish, what do you think will happen if I modify the port priority of switch 2's ports? Let's check. I changed the priority of switch 2's G103 to 6 to 0, the lowest possible value. And here are the results. Nothing changed. As the point above says, only the port IDs on the switch with the lowest system ID are significant. In this case, that's switch 1. So it's switch 1 that decides which ports are active, not switch 2. Even though switch 2 G103 to 6 have the lowest possible priority, they are still in standby. Alright, that's all we'll cover on LACP. Before we do a short quiz, here's a one-slide summary of the main points. As usual, I'll read out each point, but feel free to skip ahead if you want. LACP is an industry-standard ether channel negotiation protocol. The current standard for LACP is defined in Section 6.4 of 802.1AX 2020. LACP can be enabled in 2 modes, active or passive. Active actively sends LACP messages, and passive mode waits for messages from an active neighbor before replying. 2 useful show commands for LACP are show LACP internal and show LACP neighbor. Internal shows information about the local switch, and neighbor shows information about LACP neighbors, also called partners. LACP messages, called LACPDUs, are sent to the multicast MAC address 0180C2000002, the Ethernet Slow Protocol's MAC address. Unlike in PAGP, standalone LACP interfaces are suspended by default. They are disabled. But you can configure No Port Channel Standalone Disable on the port channel interface to change this and allow the ports to operate independently if they don't form an Ether channel. We covered a couple of LACP's key timers. First is TXWhen, which is like the OSPF hello timer. It determines how often the port transmits LACPDUs. During Ether channel negotiation, it's set to 1 second, but once the link is established, it's set to 30 seconds, the slow periodic time by default. It can be set to 1 second, the fast periodic time, if requested by the neighboring port. Then we covered the current while timer, which is like the OSPF dead timer. It determines how long LACP information from a neighbor remains valid after ceasing to receive messages from that neighbor. If the timer counts down, the neighbor is removed. It's set to 90 seconds by default, the long timeout time, but can be set to 3 seconds, the short timeout time if configured. And here's how to configure it. LACP rate fast or LACP rate normal on each member interface of the Ether channel. Keep in mind what this command actually does. It requests LACPDUs from the neighbor at the specified rate. It doesn't configure the rate at which this port will send messages, but the rate at which it expects to receive them. There are a few other LACP timers, but these are the main ones. LACP allows up to 16 links in a single bundle, with up to 8 active and the rest in hot standby mode. You can modify the maximum number of active links with LACP Max Bundle, with a valid range of 1 to 8 on the port channel interface. And you can modify the minimum number of active links with Port Channel Min links, with a valid range of 2 to 8. The default is 1, but you might want to change it if you don't want a low bandwidth port channel to remain up. We then covered the LACP system ID, which consists of a 16-bit priority and a MAC address. You can view the system ID with Show LACP SysID and modify it with LACP system priority. The default is 32768, and the valid range is from 0 to 65535. The switch with the lowest system ID determines which ports will be active. I said this before, but keep in mind that each switch independently defines its maximum and minimum links. If one switch sets a maximum of 6, but the other sets a maximum of 4, there will only be 4 active links. Then, the switch with the lowest system ID decides which 4 links will be active. And how does it decide? It uses the port ID of its ports. The LACP port ID consists of a 16-bit priority and a port number. You can modify the port priority with LACP port priority on each interface. The default is 32768, and the valid range is from 0 to 65535. Ports with a lower port ID will be active, while ports with a higher port ID will be standby. Keep in mind it's the port IDs of the switch with the lowest system ID that decide the active links. Okay, that's what we covered in this video. Now let's do a short quiz to test your understanding. Here's quiz question 1. Examine the output. Which of the following statements are true? Select 2. Pause the video now to think about your answers. Okay, the answers are A and D. You can tell A is correct because although G1, 9, and 10 have the lowest port priority, 0, they are still in standby mode. This means that the neighboring switch is deciding which ports are active, so switch 5 system ID must be higher than its neighbors. And D is correct because G101 has the F flag. Show LACP internal shows information about the local switch's ports. The F flag means that switch 5 G101 has the LACP rate fast command configured. So it expects to receive LACPDUs every second from its neighbor. C might be correct, but we don't have enough information to know. G101's neighbor might be requesting slow hellos, or it might be requesting fast hellos. This output doesn't tell us. Okay, next question. Here's question 2. Which of the following statements about LACP are true? Select 2. Pause the video now to think about your answers. Okay, the answers are C and E. C is correct because LACP ports will enter the suspended state if they can't form an ether channel. To change this, you can configure no port channel standalone disable on the port channel interface. And E is correct because the LACP rate fast command configures how often the port expects to receive LACPDUs from its neighbor. It doesn't change how often the port itself sends LACPDUs. That depends on what the neighbor requests. Okay, that's all for the quiz. And that's all for this video on LACP. We covered several new concepts beyond the basics you already learned in the CCNA. We focused mainly on the key LACP timers, the LACP rate fast command, the maximum and minimum link features, and the system and port IDs. As always, make sure to try out these features in a lab and experiment with them a bit so you can really understand how they work. I hope this video was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members who support me through YouTube channel membership. To become a member, please click the join button under the video. Thanks to Jonathan Makara, George, Gustavo Macedo, Marcel Lord, Dragos Hirnea, Zakib Shah, Mayor Salman, Mark Jackson, Bold 1C1U, GZ123, Hector Hernandez, Arpad Conives, 5 Feet, Owad, Hussein Yavuz, Samuel Tavares, Kevin Hayes, Brian Grant, Georgi Gemejev, Adelson Pereira, DMJ2, Steve Cox, Jasper Yim, Pedro Hartman, Tricky Mickey 123456, Jefferson Steelflex, Toxic, Sinan Sarisinar, Daniel Andrade, Wilmer Romero, Dragos George, Philip Jovanovic, Sunny Idigu, Mike Crumby, Hello BPDU, Mikhail Chopsky, Hemanth Jabalpuri, Dariush D, Juan Morales, Gonzalo Nicolas, Doomed Soul, Julio Maya, Egreso, Anand Abyankar, Clyde Mkorobindo, Orlando Flores, Adekola Ismail Salami, GG7, Tobe Hedin, MDS Electronarzedjia, G. Gant, Yukshika, Uma Shankar Sharma, Ali Riza Bilir, Seb Z, James Corley, Alexei Usov, Excelius, To Be Like Our Superheroes, Mohamed Balta, Tazo Gurganadze, Brandon Byers, Opsero, Mohamed, Omole Celine, Mateo Falcone, Jean-Ruby Good, Zach Ross, I'm Me 87, KB Marco, DB Foreigner, Modi, Manolo Esquivel Villanueva, Parabellum, and 21st Century Travel. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.